I'm Anil Kumar sharing with you some higher level limits question on which we are going to apply L'Hopital's rule. Now this series is good for students who are doing IB, AP or AB I wrote earlier, calculus or even university level first year, right? Now L'Hopital's rule normally is applied when we are looking forward to indeterminates of the form of 0 over 0 or infinity over infinity, right? Could be plus or minus. But you should appreciate that it is also applied when we are talking about powers, especially if we have a case where we are talking about limit x approaches a for the function f of x to the power of g of x, right? So in such cases, if we have the type 0 over 0, or if we have the type infinity over 0, or if we have the case of 1 over infinity, even then we could apply L'Hopital's rule. So these examples are taken based on this. Now the very first one is basically limit x when limit of x times ln x when x approaches 0 from the positive side. Well, ln x is a function which is defined only when x is greater than 0, right? Here you will see that we are talking about product. If I substitute 0, I get 0 times ln of 0 is infinitely large, right? So, but a negative value. So, which is minus infinity. Now, minus infinity could be written as 0 times 1 over 0, right? Maybe negative or positive. So, in a way, it is 0 over 0. So, that qualifies for L'Hopital's rule. Now, here we have 0 to the power of 0 form. And then here we have infinity to the power of 1 over infinitely large means 0. Then if I substitute 0 here for sine x, sine 0 is 0, so we get 1 plus 0 as 1. Cotangent of 0 is infinitely large, so this is of the form of 1 over infinity. And these quadratic functions, cos for 0 is 1, so that is also 1 over infinity. Here if I substitute a over a is 1, 2 minus 1 is 1. So this is also the form of 1 over infinity, right? So all these cases are the ones in which we can apply this rule and quickly find the limit. You will notice here that we don't have anything like 0 to the power of infinity, right? Nothing like this. This is actually equal to 0 only, so it is not indeterminate. These are indeterminate forms since anything to the power of 0 could be 1, right? But 0 to the power of anything is 0, so we are not very sure of, correct? So anything to the power of 0 could be 1, but infinitely large to any power, we don't know. And therefore, it is indeterminate. 1 to the power of anything is 1, but 1 to the power of infinitely large, indeterminate. So therefore, these three are the only cases which are considered as indeterminate, but not this one. Okay, so remember that. Now let's see how to solve these types of limit questions. We'll take them one by one. A. Limit when x approaches 0 from the right side for x times ln x. We could rewrite the function as limit x approaches 0 from the right side, and I could write this as ln x over 1 over x, correct? Now you can see, if I substitute 0 here, what do I get? I get infinitely large value over infinitely large value, correct? Now this approaches negative infinity. So we have something like this, which is indeterminate form. And therefore, we can apply L'Hopital's rule. So we have this limit as derivative of ln x is 1 over x. So let's write limit x approaches 0 from the right side. So derivative of ln x is 1 over x. and derivative of 1 over x is minus 1 over x square. Correct? Now this could be written as limit x approaches 0 from a positive side. So if you rearrange, we get negative of that x square goes in the numerator over x, correct? Or we could write this as limit x approaches 0 from the positive side. Let me put it in brackets. That becomes minus x. Now if I substitute 0 here, what we get is minus 0, which is equal to 0. So basically what we find here is that the limit of this function as x approaches 0 from the right side is indeed 0. Now this limit helps us to solve part B, and that is the reason why in this series I took that as my first example. Okay, now we need to find limit of this function. So we have limit x approaches 0 from the right side for x to the power of x. Now x could be written as, let me rewrite this, x could be written as an exponential function as e to the power of ln x. Perfect. E to the power of ln x is same as x. So when we substitute this, what do we get? We get this as limit x approaches 0 from the right side, e to the power of ln x to the power of x. Correct? Now that means limit x approaches 0 from the positive side, e to the power of x ln x, right? Using the power rules for exponents. Now here, you know, the limit of this function is, we could write this as e to the power of limit x approaches 0 from the positive side for x ln x. And we just now showed that this limit is 0, so we get e to the power of 0, and anything to the power of 0 is 1, and therefore this limit is 1. Now you'll appreciate this was a form 0 over 0, right? So if I substitute 0 here, we get a form 0 over 0. So that is an example of indeterminate powers of the type 0 over 0, correct? Now let's take more examples with indeterminates of powers. Now here we have limit x to the power of 1 over x. If I substitute infinity here for x, I get infinitely large over 1 over infinity, which is infinitely large over 0. Now that is also indeterminate power, correct? So we could solve this using L'Hopital's rule. Now to solve these types of questions, wherever we have this kind of situation, it is good practice to write them as an exponential or logarithmic function. So what we do here is we say, well, let y be equals to x to the power of 1 over x. In that case, ln y will be equals to ln x to the power of 1 over x. Or we can say ln y is equals to 1 over x times ln x. And now we can take limit x approaches infinity on both the sides. So we can rewrite this as limit x approaches infinity for ln y is equals to limit x approaches infinity for ln x over x, correct? So in a way, we have written it in the form where we can now apply L'Hopital's rule, right? Infinitely large over, in this case, 0, infinitely large over infinitely large, correct? So applying the rule, what do we get? So we can write this as let me do it here. It says limit x approaches infinitely large for ln y is equal to, now in this case, limit x approaches infinity. Derivative of ln x is 1 over x, and derivative of x is 1, correct? So on the right side, what do we get? We get limit x approaches infinity for 1 over x. Now, if x is very large, then this approaches 0. So we get that the limit when x approaches infinitely large for ln y is equal to 0. And therefore, the limit of y is what? So limit of y as x approaches ln y is e to the power of 0. And e to the power of 0 is 1. So we get our result as 1. And therefore, this limit is also equal to 1, right? So I hope the steps are absolutely clear. So whenever you have powers, it is a good idea to write them as natural log function, take limits on both the sides, and then find out the answer, right? So the last statement here says limit of y, and you know what y is. So basically it is limit x approaches infinity for x to the power of 1 over x, which is equal to 1, correct? So that completes this. Now let's take another example, which is based on trigonometric functions. Now let's take the limit for the trigonometric function. We need to evaluate limit when x approaches 0 for 1 plus sine x to the power of 2 cot x. If I substitute 0 here, I get 1 plus 0 to the power of infinity, right? Which is 1 to the power of infinity. Now that is an indeterminate of power type. So we could actually apply L'Hopital's rule and solve this question. Now let us try to understand this strategy, how to apply this rule. We could actually make a substitution saying y equals to 1 plus sine x over 2 cotangent x. Now if I take natural log on both the sides, I get ln y equals to ln 1 plus sine x to the power of 2 cotangent x, or we can say ln y equals to 2 cot x times, I forgot to write ln, let me write with different ink, ln 1 plus sine x, correct? We could also write this as 2 ln 1 plus sine x. Now cotangent x is 1 over tan, so we could write this as tan x here. And we have ln y. Now limit of this function, we can say, well, let's find limit of this function as x approaches 0. Okay, so that is the strategy. So first step is to write this in the form of natural log and then find the limits, correct? Now here, as you can see, if I substitute 0, then we do get an indeterminate form and we can apply L'Hopital's rule. So derivative of the numerator is 2 times. Now ln 1 plus x means 1 over 1 plus sine x times derivative of this, which is cos x, over derivative of tan x is secant square x. Now that is what we get, and the limit of this function is also the limit of derivative of the numerator and denominator. So that is L'Hopital's rule, correct? So we have limit x approaches 0 for ln y. Now we'll take it to the right side and simplify a bit. So what we have here is limit x approaches 0 for y, ln y is equal to all this. We could write this as limit x approaches 0. So we have 2 cos x, let me write like this, 2 cos x over 1 plus sine x times secant square x. Now we can substitute 0 here, right? So what do we get? So we get 2 cos 0 over 1 plus sine 0 over secant square 0, right? Which clearly is cos 0 is 1, so we get 2 here, and 1 plus 0, so we get 2 here, right? So 2 divided by 1 is 2. And that is what we get as limit when x approaches 0 for ln y, correct? So that is what is the limit for our ln y. Now, ln y, we have written y in the form of, y is written in the form of e to the power of ln y, correct? Since we wrote y as e to the power of ln y, we could actually now rewrite this back to the way the question is, and we can say limit x approaches 0 for 1 plus sine x to the power of 2 cot x. That is what y is, right? Is equal to the limit of y for y itself. Is that okay? Which is same as equal to the limit as x approaches 0 for e to the power of ln y, correct? Which is, in our case, e square. So that is how we could get. Or at this stage, so the alternate is, at this stage, we can straight away write down from here that limit x approaches 0 for y is equal to e square, where y is equal to the function. Do you see that? So I prefer this method. I prefer moving from here to this stage, correct? So now we get our answer that this limit is e square, correct? So that is how you could actually solve trigonometric functions with exponents leading to infinity. So we'll take up the next example. So let's evaluate now the limit of cos x to the power of cotangent x when x approaches 0. You can actually pause the video, answer this question, and then look into my suggestions since we have done a similar one earlier. So first step is write this as y equals to cos x to the power of cotangent x. Now take natural log both sides. So we get ln cos x to the power of cotangent x. Or we can say ln y equals to cot x times ln cos x. And this could be written as ln y equals to ln cos x over, so cotangent is tan, so we'll write this as tan x. Now at this stage, we'll take limit on both the sides, and we'll write this as limit x approaches 0 for ln y equals to limit x approaches 0. Now whenever we're talking about this function, it is because we're taking natural log, we have to consider from the positive side. So what we get here is limit of ln cos x over tan x. Now applying the log capitals rule, where the limit of the ratio of functions is same as limit of their ratio of their derivatives, right? So we'll write this as limit x approaches 0 for ln y will be equal to limit x approaching 0. The derivative of cos ln cos x will be 1 over cos x times derivative of cos x, which is minus sin x, divided by tan x, which is secant square x. So we get here that limit x approaches 0 for ln y is equal to strictly speaking, whenever we are doing these questions, we should have written from the positive side, right? Since this strategy, taking natural logs, is only valid when the values are positive, right? So that's the domain of y. So, well, while writing the questions, I didn't write that, but that should be taken as a note. Okay, so let me write this as positive, right? So we have limit x approaches 0 from the right side. Now here what we get is minus sine x over so let me write this as minus, now that is cos square x. So what we get here is minus sine x times cos x. Correct? Because one of them gets cancelled. And if I substitute 0 here, then sine of 0 is 0. So we get this limit as 0. So we have limit x approaches 0 from the right side for ln y is equal to 0. And therefore, we can now rearrange and write this as limit x approaches 0 for y is equals to e to the power of 0, which is 1. And therefore, the limit of the given function is actually 1. So we have answer as 1. Correct? So let's take the next question, which is the last question of this series. We have a limit when x approaches 0 for 2 minus a over x to the power of tan pi x over 2a. Now in this particular case, if I substitute a here, I get 2 minus a over a, which is 1, to the power of tan pi a over 2a, right? Which is same as 1 to the power of tan of pi by 2, which is infinitely large. So it is 1 to the power of infinity. So this is a case of indeterminate powers. So we'll actually be very specific. We will approach a from the right side, since we are using logarithms to solve these questions. Okay, so let's do the same method, which is writing this as a natural log. So we say y equals to 2 minus a over x to the power of tan pi x over 2a, right? Taking natural log both sides, we have ln y equals 2. So you get tan pi x over 2a times ln. So I've cut down one step here. We could write like this, correct? Now, we'll consider from the positive side. So we can say now limit x approaches a from the positive side for ln y is equals to limit x approaches a from the positive side. Now tan pi x by 2a, we'll take it in the denominator. So write limit this is ln, sorry, ln 2 minus a over x over cotangent pi x over 2a. Perfect. So now we know from L'Hopital's rule that limit of the ratio function is same as limit of their derivatives, right? So we'll use that rule now. So say limit x approaches a from the right side for ln y equals to limit x approaches a from the right side. Now let's write down the derivative of this function. So it is 1 over 2 minus a over x times derivative of minus a over x, which is a over x squared, correct? Okay, and the denominator here is derivative of cotangent pi x over 2a, so that is minus cosecant square pi x over 2a times the derivative of this inside function. So it is pi over 2a, correct? So that becomes the derivative of this particular function. Now we can write this as limit x approaches a from the right side for ln y equals 2. So we'll just rearrange this. So we have a over x squared, and here we have divide by pi over 2a. So I'm writing this as, when we flip it, we can write this as 2a over pi, okay? We could write this as 2a over pi, and then we have here negative sign, so I made negative 1 here. So we have cosecant square pi x over 2a, and then we have all this, which is, okay, let me keep it in the numerator, 1 over 2 minus a over x. Okay. Now, if I substitute, let me write again. Limit x approaches 0 for ln y is equals 2. So this expression here is 2a square over x square pi, correct? This expression here, let me rewrite this, is negative. So I'm writing negative here now. 1 over, this is 2 minus a over x, correct? So I wrote this in the denominator times cosecant square pi x over 2a. So basically I rewrote it. Okay. Now let us substitute x equals to a. It is approaching a from the right side. So we get limit x approaches a from the right side for ln y is equal to. So if I write a here, I get minus 2a square over a square pi, and here I get 1 over 2 minus a over a, which is 1, right? Times cosecant square pi and a cancel, so we get pi by 2, correct? Now cosecant pi by 2 is 1 and a over a is also 1, so denominator is 1, correct? Here a square cancels, this a square cancels, so what we are left with is minus 2 over pi. Perfect. So we are left with minus 2 over pi. Therefore now we can write the limit when x approaches a from the right side for y equals to e to the power of minus 2 over pi. Do you see that? So that becomes our answer. So the limit of this function is e to the power of minus 2 over pi. So with this we conclude the series where we have taken 6 examples mainly to explain if we have a situation where we have indeterminate of the form of powers, in that case how can we solve these questions, correct? So I hope the concept is clear to you. Let me understand the concept which should be followed in solving such questions. I'm Anil Kumar. You can always share my videos, subscribe to them, and if you like, that'll be great. Thank you and all the best.